Chapter 14 in our textbook is entitled Chemical Kinetics. We're about to enter a series of chapters where we describe the nature of a chemical reaction. One set of descriptions will involve knowing the extent to which a reaction takes place. In other words, whether a reaction will produce large reaction yields. One such description speaks to how quickly a reaction takes place. And one speaks of the energetics required or associated with a chemical reaction taking place. The term chemical kinetics, the focus of chapter 14, deals with the speed or how quickly chemical reactions take place. The speed at which a reaction takes place or occurs is known as the rate of reaction or the reaction rate. An undertaking of the study of reaction rates is known as chemical kinetics. And the study of reaction rates is incomplete unless we include a step-by-step pathway from reactants to products. Such a view is known as a reaction mechanism. Now, there are several important factors that can affect the rate of reaction. The physical state of the reactants, whether they're in the solid, the liquid, the gas, or an aqueous solution. The concentration of the reactants, the temperature of the reaction, and the presence or absence of a catalyst. It's important for us to understand how these factors can affect the rate of reaction. First, let's consider the physical state of the reactants. In order for a reaction to occur, we must see the reactants colliding with one another. The more readily the reactants collide, then the more rapidly they react. Well, we tend to find that in the gas phase and in the liquid phase, reactions tend to take place more rapidly. Even in the solution phase, aqueous species can find one another more rapidly than they can in the solid phase. Solid phase reactions tend to be much slower. An instance in which we see an increase of the rate of reaction in the solid phase is when the solid has an increased surface area. In other words, a fine powder that has more surface area than a pellet or a nugget or a tablet of the solid in question. The effect of reactant concentration seems to be relatively straightforward. If you have a higher reactant concentration, then there is more reactant to go around. More reactant means that these reactions will likely take place at a faster rate. So we generally see an increase in reaction rate as we increase the concentration of our reactants. When considering temperature as a factor, the general understanding is that the reaction rate increases with increased temperature. By increasing the temperature, you're increasing the average kinetic energy of the molecules. And at higher temperatures, since the molecules move more quickly, that effectively is going to increase the number of collisions as well as the energy that the molecules possess during these collisions. By definition, a catalyst is a substance that affects the rate of reaction without itself being consumed. The purpose of a catalyst is to change the pathway or the mechanism by which a reaction takes place. It essentially lowers the energy barrier, making reactions take place more readily. We see that catalysts are very important in many biological reactions. Now, the speed of a reaction or the rate of reaction is defined as a change in concentration over a given period of time. We oftentimes monitor the concentration of a reactant or a product over an elapsed period of time in order to determine how quickly a reaction proceeds. Now, there are various types of rates that we can measure. the average rate of reaction over a long period of time, the instantaneous rate or reaction, where we determine the rate of a reaction at a particular moment, and the initial rate of reaction, the rate at which a reaction begins. It should be noted that for several reactions, the reaction tends to slow down over time. That's because the concentration of the reactants decreases as a reaction takes place. So where there is a dependence upon concentration, we see that the initial rate of a reaction could be quite different than the final rate of reaction. Let's take into consideration the following reaction. The reaction of butyl chloride with water in order to form butyl alcohol, also known as butanol, and hydrochloric acid. Now, in order to determine the rate of the reaction or how quickly the reaction is taking place, we're going to pick either a reactant or a product and determine how that concentration changes over a given amount of time. Since we start with an appreciable amount of butyl chloride, we're going to measure the rate of reaction by looking at how quickly butyl chloride is consumed or is used up. We could also look at butanol and see how quickly butanol is formed. But as it stands, if we look at the consumption of butyl chloride, we see that over time, our concentration is going to lessen. We're going to get less butyl chloride over time. So if we look at the change in concentration, we're going to start with a high concentration and we're going to end up with a lower concentration. Since change is equal to final conditions minus initial conditions, then that change would be negative. In order to compensate for that negative, and so that we don't have a negative speed or a negative rate, when we're looking at the consumption of reactants, the rate of reaction is equal to the negative of the change in concentration over a given amount of time. Let's take a look at some reaction rate data. We have observed the concentration of butyl chloride over a given amount of time. And as it is consumed, we can calculate a rate for each elapsed period of time. Between time 0 and time 50 seconds, we see that the concentration has decreased from 0.1 molar to 0.0905 molar. If we employ that calculation, then we will determine that the rate of reaction over the first 50 seconds is 1.9 times 10 to the minus fourth molar per second. In other words, we have lost 1.9 times 10 to the fourth moles per liter of butyl chloride per second. As the reaction continues, we see that the average rate of reaction tends to decrease. A significant reason behind that is that we do not have as high a concentration of butyl chloride each step along the way. So since we have less and less reactant, it's going to take time, more and more time, for our reactants to find one another and allow for the reaction to take place. We can see that by the time we get down to 500 seconds, that the reaction rate has decreased significantly. After 10,000 seconds, we see that the concentration of butyl chloride is 0 moles per liter. There's no remaining butyl chloride. Therefore, the rate of reaction has decreased to 0. We do not see the reaction taking place any further. What we just took a look at was a measurement of the average rate of reaction. By looking at the change in concentration over an elapsed period of time, whether it be 50 seconds, 100 seconds, 800 seconds, then we can determine overall an average rate of reaction. But by plotting the data, we can get more information about the rate of reaction. Here we see a graph where we have plotted the concentration of butyl chloride versus the time. We see a constant decrease in the concentration over time. Well, that matches up with what we know to be true. The reactant is being consumed over the course of the reaction. If we look at the slope of the slope of the curve is constantly changing. If we look at the slope of the curve at any given point in time, that will tell us the rate of change at that point in time. That rate of change is known as the instantaneous rate of reaction. Now, if we look at the slope of the line that is tangent to the curve at time zero, that is the initial rate of reaction, how the rate takes off immediately. This is oftentimes very interesting to chemists in studying chemical kinetics. Now, it should be noted that as we follow the course of a reaction, whether we look at the concentration of a reactant or the concentration of a product, we should still be able to chart the rate of reaction. It is important to note a few things. The rate of reaction is very much dependent upon stoichiometry. We'll get an understanding of that in subsequent slides. But if we follow the rate of production of a product or the rate of consumption of a reactant, we should know that those values will be the same, but they will be opposite in sign. The change of butyl alcohol is going to be positive. The change in butyl chloride is going to be negative. So once again, we account for that by making the consumption a negative value. Taking a negative and multiplying it by a negative gives us a positive. So our rate of reaction is going to always be a positive number. Well, that's all fine and dandy when we deal with stoichiometry of such a simple variety. In the previous example, we saw 1 mole of butyl chloride reacting with 1 mole of water in order to produce 1 mole of butyl alcohol and 1 mole of hydrochloric acid. But what if the stoichiometry didn't reflect a 1-to-1 molar ratio? What would the rate of reaction be for the following reaction? Here we see 2 allotropes, or naturally occurring forms of oxygen. Triatomic oxygen, otherwise known as ozone, and diatomic oxygen, the oxygen that we know and love and breathe. 2 molecules of ozone will react in order to form 3 molecules of diatomic oxygen. So the rate at which ozone is consumed is not necessarily the rate at which oxygen is formed. If we look, we see that by the time 2 moles of ozone are consumed, 3 moles of oxygen have been formed. So the rate at which these take place, if we observe the change in concentration with respect to time, is going to be different. So how do we account for that? We use the stoichiometry of the reactants and products in question in this fashion. In a very general sense, we see that for the reaction of A and B to form C and D, with the lowercase letters representing the stoichiometric coefficients of the compounds represented by the capital letters, the rate of reaction when dealing with products and reactants is given by the following. Now, please note that the rate of reaction with respect to A and B are both negative values. Again, we're dealing with the consumption of our reactants. The rate of reaction with respect to C and D is indeed positive because we are seeing the formation of our products. Now, in general, the rates of reaction tend to increase when the reactant concentration is increased. Conversely, the rates tend to decrease as the concentration of the reactants is reduced. So how do we determine what effect the concentration of each individual reactant has on the rate of reaction? Well, we perform a series of experiments, and in these experiments, we keep the concentration of everything constant except for one reactant in order to see what happens to the rate. After we determine the effect that that concentration has on the reaction rate, then we move on to a different reactant. And we do this until we have seen the effect of each and every reactant on the rate of reaction. For example, let's consider the following reaction. The reaction of the ammonium cation in solution with the nitrite anion in solution in order to form nitrogen gas and liquid water. Here we see the results of 6 different experiments, all in which we started with different concentrations of ammonium and nitrate. We observed the initial rate of reaction, in other words, that instantaneous rate of reaction at the very beginning of the reaction. We do this in an attempt to observe exactly how quickly the reaction takes place based on the amount of each reactant. But between each experiment, you will notice that we have changed the concentration of one of the reactants. In the first 3 experiments, we keep the concentration of nitrite constant at 0.2 molar, and we change the concentration of the ammonium cation. In experiments 4, 5, and 6, we hold the concentration of the ammonium cation constant at 0.2 molar, and we change the concentration of our nitrite anion. It's important that we look at how the concentrations change and the effect that that has on the observed initial rate. If we look at experiments 1, 2, and 3, from experiments 1 to 2, we see that we double the initial concentration of ammonium. The observed initial rate of reaction similarly doubles from experiment 1 to experiment 2. When we perform experiments 2 and 3, we see that once again a doubling of the concentration of ammonium results in a doubling or an approximate doubling of the rate of reaction. We see the same general trend with the nitrite anion in experiments 4, 5, and 6. By doubling the concentration, we see a doubling of the initial rate. And this speaks to a specific classification of reactions with regards to chemical kinetics. With this information, we can compare the initial rates of reaction and determine the dependence of the rate of reaction upon the concentration of each individual reactant. So by doing this one at a time, taking each reactant, holding one reactant constant while changing the concentration of another, we can see the effect that changing the concentration will have on the initial rate of reaction. So with the following formula, we see that comparing the rate of a reaction under a certain set of conditions with the rate of reaction under a different set of conditions, with a different concentration of reactant, that this ratio comes out of the method of initial rates. And what this ultimately tells us is the dependence of the rate on the concentration. Now that is going to be reflected in what we call the reaction order. In the first 3 experiments, we saw that we kept the concentration of nitrite constant. We also saw that as the concentration of ammonium doubled, so did the rate of reaction. So using that information in our equation, we see that the rate of reaction suggests a reaction order with respect to ammonium of 1. Similarly, in reactions 4 through 6, when we held the concentration of ammonium constant, we saw that by doubling the concentration of nitrite, we also saw a doubling of the rate. Therefore, employing the equation and the method of initial rates, we see that the order of reaction with respect to nitrite is also 1. So we saw that in experiments 1 through 3, that by doubling the concentration of ammonia, we saw a doubling of the rate. We saw the effect that changing the concentration of ammonia had on the rate in the first 3 experiments. We saw the effect of changing the concentration of nitrite on the rate in the last 3 experiments. We use all of this information together to develop what we call the rate law, which is an expression that shows the relationship between the rate of reaction and the concentration of all reactants. The rate law expression typically looks like this. The rate is equal to K, which is the rate constant, times the concentration of each reactant raised to a power. Now you'll notice that the power that reactant 1 is raised to is X, reactant 2 is raised to the Y. We will soon understand that these exponents refer to the order of reaction, something that we essentially calculated on the previous slides. So, since we determined the order of reaction with respect to both ammonium and nitrite to be 1, or first order, the reaction rate expression, or the rate law expression, is given by the following equation. Now, once again, it should be noted that those exponents, the x and y that we previously saw in the rate law expression, tell the reaction order with respect to each individual reactant. We saw that the reaction was first order in ammonium. It was also first order in nitrite. Overall, the reaction would be considered second order, because we simply add up the reactant orders of all the reactants to get the overall reaction order. Again, it should be noted that the value of K is a rate constant, and that is a temperature-dependent quantity. I can't stress this enough. The order of reaction is not something that you can determine by looking at the stoichiometry. Please, 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 please do not look at the stoichiometry of a reaction and consider that to speak to the order of reaction. The order of reaction must be determined by using the method of initial rates, by comparing the rates of reactions while changing the concentration of one of the reactants in question and seeing the effect that it has on the rate. Here we see 3 different reactions with vastly different stoichiometries. And note that the stoichiometries have absolutely nothing to do with the exponents in the rate law expression. Now, the relative value of K can be an indicator of the rate of reaction. For reactions where the rate constant is greater than 10 to the 9th power, or 1 billion, the reaction is considered to be quite fast. For reactions where the K value is less than 10 to the 9th power, the reaction is considered to be slow. Some reaction rates are only dependent upon the concentration of one reactant. They're independent of all other reactants. These reactions are said to be first order reactions, and the rate law simply reflects the rate with respect to that particular reactant. On the right hand side of the slide, we see a compound called methyl isonitrile. Methyl isonitrile undergoes a conversion to acetonitrile by means of a first order reaction. What is the relationship of the rate constant to the concentration of a species in a first order reaction? Well, if we look at the rate expression via the rate law, we see that the rate is equal to K times the concentration of A. At the same time, the rate is given by the change in concentration of A with respect to time. So by equating these two things, we can rearrange the equation in such a fashion that we see that the change in the concentration of A over the concentration of A at a specific time is equal to the negative rate constant times the time elapsed. If we integrate this, then we come up with the expression where we see the natural log of the ratio of the concentration at any given time divided by the initial concentration, what we call A naught, is equal to negative K times T. Now, I know that may have involved a lot of math, but just stick with me just a little longer. If we rearrange that last expression, then we see that the natural log of the concentration at any given point is equal to negative K times T plus the natural log of the initial concentration of reactant. When looking at this, we see the parallels between y is equal to mx plus b, which is the equation of a line. So if we were to plot the natural log of A versus temperature, then we would see a line, a straight line. Here we see further evidence that the conversion of methyl isonitrile to acetonitrile is indeed a first order process. If we look at the left graph, we see the relationship between pressure and temperature. Now, knowing what we know about our gas laws, ultimately we can see a correlation between pressure and concentration. The more gas that is present, the greater the pressure it exerts. So by seeing a decrease in the pressure, we're also seeing a decrease in concentration. That's what the left graph suggests. But on the right graph, we see the natural log of that pressure, which again is a reflection of concentration, versus time, giving a linear plot. So since the plot is indeed linear, the reaction would be considered a first order reaction. Now we can use that plot in order to determine the value of our rate constant. Once again, if we consider y is equal to mx plus b type behavior, then if we plot that line, the slope of the line will be negative k. Now, while undertaking the study of kinetics, we need to introduce the concept of the half-life. By definition, the half-life is the amount of time that it takes for 1/2 of a reactant to be used up in a chemical reaction. And for a first order reaction, the half-life, which is given by T sub 1/2, can be found by using a series of equations. If we follow these equations to their conclusion, then we will ultimately see that for a first order reaction, that the half-life, or T sub 1/2, is equal to 0.693 divided by the rate constant. So the half-life is dependent upon the rate constant with this expression. When considering second order reactions, we must understand that there are two types of second order reactions. There are reactions that are second order in that they are dependent upon the concentration of one species squared in the rate law expression. If we want to look at the relationship between the rate constant and the concentration of reactant for this type of second order reaction, then we start with the idea that the rate is equal to K times the concentration of A squared, as is given by the rate law expression. At the same time, the rate is still equal to the change in concentration over the time elapsed. So if we equate these two, then we can follow the math to the last equation listed, which suggests that 1 over the concentration of A is equal to 1 over the concentration of A initially, or A naught, plus KT. Now, if we simply reverse the two components on the right-hand side of that equation, we again could see a y is equal to mx plus b situation, where 1 over a is y, m is equal to k, b is equal to 1 over a naught, and x is equal to t. So ultimately, if we plot 1 over the concentration with respect to time, then the slope of that line would be given by k, and the y-intercept would be 1 over a naught. It should be noted that the linear relationships for first order reactions and second order reactions are different. In the case of a first order reaction, we saw that a line sloped downward. In the case of a second order reaction, we're going to see that the line slopes upward, represented by, in a first order reaction where the slope was given by negative k, whereas in the second order reaction it is given by a positive k. Here we see an example of a second order reaction that involves one reactant, the decomposition of nitrogen dioxide. If we plot the natural log over time, we see that we do not get a linear trend. We still see a curve. So that suggests that by plotting the natural log versus time, that we do not have a first order reaction. Instead, by plotting 1 over the concentration with respect to time, we do see a linear trend, and that line does point upward. So this is evidence that this reaction is indeed a second order reaction. So now we want to take a look at how the half-life can be determined for a second order reaction of this type. Using the following integrated rate law, we use the mathematics to determine exactly what the value of t sub 1/2 ultimately will be. And at the end of the day, stick with me folks, we see that t sub 1/2 is related to the initial concentration of our species as well as the rate constant. So now we see an example of a rate constant having an effect on the half-life as well as the initial concentration having an effect on the half-life. In the case of a first order reaction, we only saw that the value of K contributed to the half-life. But here we see not only the value of K, but also the initial concentration being a factor. It should be noted that there is a second type of second order reaction, one in which we see the rate depending upon two different reactants, each raised to the first power. The example that we saw previously of ammonium and nitrate, where each reactant is first order, combined to give a rate law for a reaction that is considered to be second order overall. Now, there are actually examples of reactions that are independent of the concentration of the reactant. Regardless as to how much reactant is present, the reaction is going to proceed at a constant rate. These reactions are said to be zero order reactions. And essentially, the reactions are linear in their concentration. We're going to see a constant decrease in the concentration, meaning that as they are consumed, the concentration has no effect on the rate of reaction. Now, there are a few things that we need to consider in determining a model for whether or not a reaction will take place at an appreciable rate. Temperature is a factor. The frequency of collisions, how often molecules collide. The orientation of the molecules, in other words, if the molecules are oriented in such a fashion that will promote a reaction, and the energy needed in order for the reaction to take place, a quantity that we will ultimately call the activation energy. Now, as I previously stated, in general, as the temperature increases, the rate of reaction will increase. The rate constant, the value of K, is indeed temperature dependent. At higher temperatures, once again, the value of K increases. Typically, the rate constant doubles for every increase in temperature of 10 degrees Celsius. Now, there are various models to consider in determining whether or not a reaction will take place. The collision model is based on the kinetic molecular theory, having the same root as the kinetic theory of gases that we spoke of earlier. In order for molecules to react, they must collide. The more collisions there are, the more reactions can occur. So if we have more molecules, in other words, a higher concentration, then the rate of reaction is likely to be faster. In a chemical reaction, bonds have to be broken and new bonds have to be formed. And these things can only happen if molecules collide with one another. This is the basis of the collision model. With that being said, sometimes molecules can collide without forming products. The molecules have to be aligned or oriented properly in order for chemical reactions to take place. If the bonds must be broken and new bonds formed, the atoms need to be in the appropriate positions in order for new molecules to be formed. Now, for a reaction to take place, there is a certain amount of energy at a minimum that is required. This energy is called the activation energy. And it's essentially an energy barrier that needs to be overcome in order for a reaction to take place. If we think about energy as being a hill, in order to see a reaction take place, we have to get over the hump. Furthering this model, we see the idea of a transition state. As reactants gain energy while the reaction proceeds, we're going to see the particles reach a maximum energy state. At this point, the atoms organize themselves into a very high energy state known as a transition state or an activated complex. And once the activated complex has been formed, then it's all downhill from there. If we essentially put the minimum amount of energy into the reaction in order to get to that energy peak, we see that as we go downhill, then we're going to achieve an energy minimum, the baseline of which is going to tell whether the reaction is an endothermic reaction or an exothermic reaction. If you put in a certain amount of energy and you get more energy out, then the reaction is considered exothermic. If you put energy in and you don't get as much energy out in the formation of products, then that is an endothermic reaction. And when we look at temperature, temperature is a measure of the average kinetic energy of all the particles that make up a given sample of matter. In the case of gases, we see that gases tend to have an average temperature, but each individual molecule does indeed possess its own energy. At higher energies, we see that more molecules will possess the energy required for a reaction to occur. Svante Arrhenius determined the relationship between activation energy and temperature. The activation energy can be determined graphically by plotting the following equation: the natural log of K being equal to the negative of the activation energy over RT, where R is the ideal gas constant, having a value of 8.314 joules per mole Kelvin, times the temperature in question. If you add the natural log of the concentration of A, then we can rearrange that equation to give the following expression. Since that expression falls under the guise of y is equal to mx plus b, once again, plotting the natural log of K versus 1 over temperature will give a straight line whose slope is negative EA, or the activation energy, over R, where R is, again, that ideal gas constant. Now let's turn our focus to the idea of reaction mechanisms. Mechanisms are those step-by-step pathways that allow us to get from reactants to products. In some instances, reactions may occur all at once, or sometimes through several discrete and measurable steps. Each of these processes is known as an elementary reaction or an elementary process. Here we see a series of examples of elementary reactions and the rate laws associated with them. If we look in a very general sense at the elementary reactions and the rate laws, then similar to the order of a reaction, we can talk about the molecularity of an elementary reaction. A first order reaction would be akin to a unimolecular elementary reaction. A second order reaction would be akin to a bimolecular elementary reaction. And a third order reaction, one that we haven't spoken of, would be equivalent to a termolecular elementary reaction. Now, in the same way that we didn't speak of third order reactions, the idea of a termolecular elementary step might seem a little out there. A termolecular step would require 3 different molecules to align properly with the appropriate amount of energy and all collide at once. These are quite rare. So if these are to take place, then they must be slower than unimolecular or bimolecular steps. With that being said, nearly all mechanisms use only unimolecular or bimolecular reactions. If the mechanism of a reaction involves the step-by-step pathway to get from products to reactants, or rather from reactants to products, the sum of all of those steps gets us the overall reaction. Therefore, the rates of all of the individual steps must sum up to be the rate of the overall reaction. The reaction can't occur any faster than any individual step. In fact, the slowest step in a reaction mechanism is said to be the one that determines the overall rate of reaction. We call that slowest step the rate determining step. I want you to imagine the following scenario. You're on the 5th floor of a building. My instructions to you are to walk down to the 1st floor, walk to your car, drive for 500 miles. After 500 miles, you're going to see another building, and I want you to walk to the 5th floor of that building. Now, the entire process is going to take a lot of time, but some steps are going to take less time than others. If you were to walk down 4 flights of stairs from the 5th floor to the 1st floor, and then you are to get in your car, and then you are to drive 500 miles, and then you are to get out of your car, and then you are to walk up 4 flights of stairs to get to the 5th floor of the final building. The step that is going to take the longest, the slowest step in the bunch, is going to be driving those 500 miles. It's not going to take a lot of time to go from the 5th floor down 4 flights of stairs. It's not going to take time to get from the bottom of the stairs to your car. It's not going to take time for you to get out of your car. And it's not going to take a lot of time for you to go from the 1st floor of the building up 4 flights of stairs to the 5th floor. But it will take you a lot of time to drive those 500 miles. That is the rate determining step. How quickly does this entire process take place? Well, it all depends on how quickly you can drive 500 miles. Please be safe. Please be safe. Well, how do we determine if a reaction mechanism is actually plausible? Well, the rate law must be able to be devised from the rate determining step. That slowest step is essentially what we're going to base the rate law on. Also, the stoichiometry must be obtained when all of the steps are added up. When you add up all of the reactants and the products, all of the steps that it takes to obtain that must give us the appropriate stoichiometry. And like any other equation, each step must be balanced. All of the intermediates, things that are formed along the way, must be consumed. And any catalyst that is used must be regenerated. Here we see a reaction mechanism with a slow initial step. In the grand scheme of things, the reaction that we want to consider involves the combination of nitrogen dioxide with carbon monoxide in order to form nitrogen monoxide and carbon dioxide. If we determine that the first step of this reaction is the rate determining step, and the rate law of this reaction is second order in nitrogen dioxide, then the first step of the mechanism involves nitrogen dioxide reacting with nitrogen dioxide. Well, this first step would result in the formation of nitrogen monoxide and a nitrogen trioxide. Now, since this is not what we want to see in the final reaction, we're ultimately going to see that nitrogen trioxide disappear as an intermediate. It forms during the reaction, but it must be dealt with. It needs to be consumed in the next step. And the next step is going to be a faster step, one in which we see the reaction of this intermediate with carbon monoxide in such a fashion that nitrogen dioxide is formed and carbon dioxide as well. If you add up all of the individual steps, or rather both of the individual steps, then you will get the overall stoichiometry of the reaction that we want to achieve. Each step balances out, the first step being the slowest step, so that gives us the rate law. This is indeed a plausible mechanism. Now, in the previous example, I mentioned an intermediate. Intermediates are formed during the course of a reaction, but they are consumed by the time the reaction is over. It should be noted that an intermediate is not the transition state. Transition state is not a stable form. Intermediates are indeed stable. And in some instances, it's possible to even isolate or identify an intermediate. A catalyst is a substance that increases the rate of reaction by decreasing the overall activation energy of the reaction. A catalyst will essentially change the mechanism by giving an alternate pathway, an alternate means of getting from reactant to product that involves less energy overall. So it makes the reaction happen more easily. It doesn't affect the energy of the reactants. It doesn't affect the energy of the products, but it does affect the energy in between of the transition state or the activated complex. So it lowers the overall energy hump that must be overcome. Three common types of catalysts include homogeneous catalysts, heterogeneous catalysts, and enzymes. The term homogeneous tends to suggest one phase or the same origin, same phase. So a homogeneous catalyst is in the same phase as the reactants. So if you have a liquid-based reactant, then the catalyst being a liquid would be a homogeneous catalyst. Sometimes the reactants and the catalyst are dissolved in the same solvent. So if we were to see an aqueous-based solution, then a catalyst that was dissolved in water be a homogeneous catalyst. In short, a heterogeneous catalyst is one that is in a different phase than the reactants. Sometimes we could see gases reacting by passing them over a solid catalyst. Enzymes are biological catalysts. Most enzymes are large protein molecules whose molar masses are in the range of 10,000 to 100,000 atomic mass units. Enzymes are typically capable of catalyzing very specific reactions. For example, catalase is an enzyme that's found in blood and liver cells. It can catalyze the decomposition of hydrogen peroxide into water and oxygen. This reaction is very important in removing peroxide, which is a potentially harmful oxidizing agent. The enzyme catalyzes the reaction at what's known as the active site, or the region where the reactants will attach. The substances that undergo the reaction at the active site on enzymes are called substrates. And that, ladies and gentlemen, is the end of our chapter 14 discussion of chemical kinetics. I find it funny that the chapter that talks about the rate of reactions, or how quickly reactions take place, was probably the lecture that took the longest for you to listen to. Oh well, thanks for your time. Thanks for your attention. Have a wonderful day. That's it.